Yeah, like Doug mentioned, I got hired by the CAC fall of 2016 to replace Lee Meltzker. Lee was a forecaster around the Eisenhower Tunnel for 23 years, and he's a hard act to follow. He's very smart, very sharp, so there was a lot of information and institutional knowledge I needed to go and fill out. And that's what we're going to talk about in the first part. Second part, we're going to look at videos and look at different ways of actually looking at videos of avalanches, and I hope you're going to enjoy it. Before I start, there's a few folks I need to acknowledge that helped me with all sorts of those projects. And yeah, how many of you guys know Coop around here? Yeah. If you're wondering where I found this picture, it's in Andy's website, and it also says next to the avalanche expert on that website, which is not Coop, by the way, that it says, we brought together the best instructors in wilderness and remote medicine, as well as Mike Cooperstein. This work, what I'm going to show you guys, is basically it's a byproduct of several personal failures. The first failure is me learning English, and here I like to actually take the time and apologize to Carl Birkland for years and many emails of awful English. The reality is I learned my English from watching sitcom, and I never really got the hang of it. But I didn't realize how bad it is till a few years ago when I went to visit Israel, my home country, and I realized that instead of improving my English, I'm just losing my Hebrew. So I decided to cut my losses and learn computer language. The second failure is me just, I can't really fall asleep on snowy nights, so I have too much time on my hands and I need to do something with it. And the third one was in January 10th, 2017. 2017 started with a bang. Two powerful snowstorms between January 4th and January 10th left us with in more than 3 inches of snow water around the Eisenhower Tunnel. On January 5th, we did avalanche mitigation work on Bethel, which is a very big path above I-70, with no substantial results. On January 9th at 9:30 in the evening, the wind switched northerly on the spider slide just west of Vail Pass, again above I-70. And 2:30 in the morning, I got a phone call from the CETO dispatch telling me that spider slide slid to the road, buried 3 westbound lanes, and shortly after that, 18-wheeler ran into the debris, and almost immediately, this picture made its way to Facebook. In the morning, we sent a small team to do gas leak mitigation on Bertha Pass and Loveland Pass, and we decided to put most of our efforts to try to protect I-70, which is the main corridor. So this is the area around the tunnel, and this is Vail Pass, you guys, just for reference, or where it's in Vail Pass. Since we shot the east side of the tunnel a few days earlier, and Bethel didn't really slip to the road since 1986, we felt pretty good about it, and we decided to put most of our effort on the west side of the tunnel. And we got busy pretty quick. This is a pretty small slide path. It's called the A slide. We typically shoot it with a howitzer. This day, the entrance to the storage area where we put the howitzer on that side of the tunnel was buried underneath 5 feet of snow and a broken plow. So we use a avalancher, and we got pretty big slide. This slide buried all 6 lanes, 15 feet deep and 200 feet wide. And as this happened, the phone keep on ringing all the time. Text messages, people want to know what's going on. Including this phone call from the guys on Bertha Pass. They basically describe what they see here, and they say they have a hard time working because cars keep on coming from the other side of the path. They try to call those guys. Yeah. They tried to call those guys, and they didn't know who to talk to, so they called me, the only guy that doesn't speak English, and asked me to take care of it. In the meantime, on the east side of the pass, one of the reasons we love I-70 so much, because it's busy. And it takes only a few minutes for the traffic to back up way back and underneath Bethel, which you can see here highlighted. So here on the east side of the tunnel, this is where we close the traffic so we can work on the west side, and the traffic backed up pretty quickly. And at 11:20, Bethel went naturally and dusted the road. And shortly after, it gained glory and fame on the social media.
The highway was open when that picture was taken?
Well, the highway was closed, but the closure was west or beyond that slide path. And we just had basically people parking underneath it, not just driving. Yeah. So it didn't feel like a very successful day at the end of that day. So I thought, try to figure out what I can do better, how I can actually try to minimize that institutional knowledge gap that we created. And I came with a few ideas, and I got Ethan's support to run with it. So the first thing we did, I look at our database of avalanches, and we have well over 150,000 avalanches in our database. I cleaned it up. Most of it is not very good, and came up with those slide paths that we care about for our highways. And we have enough good data. And I started building thresholds for what it takes for those avalanches to hit the road. So this is just one example for the Seven Sisters area. Here you see, it's basically a plot box. And you see in green are those avalanches that we shot and didn't hit the road. The red are the one that hit the road. And what I'm looking here is the 6 hour, 24 hours, and 48 hour SWE before we shot those avalanches, and what's the difference. So just those plot box, people don't used to look at it. This is basically the minimum, the maximum. This is the middle 50% of the data of the population. The notch is, the line is the average, and the two edges of the notch here and here are the 95% confidence interval. So we built this information for our slide path groups for the highway, and we did the same thing with for wind. Again, 6, 12, and 24. We look at wind speed and wind direction, and we chart it out. Here you can see the chart. You can see there's a good difference in between for the Seven Sisters for 6 hour wind direction, for example. And now we have that information. It's pretty simple to basically build a small system that goes and pull data from the weather station every hour, look at what happened in the last 48 hours, and then the next 24 hours for weather model, and build some sort of a warning system to chart it and see where we at. Let's look at what the weather is doing from that angle of how it's affect our avalanches, or size of avalanches. So here you see what we did for wind. Again, 6 hours, 12, and 24 hours. The direction is pretty clear. The black dot is actually what happened from weather station. The blue is what's going to happen in 12 hours from the weather station and weather model. And then, the green and the blue is in 24 hours. If it's actually hit the red area, it means we are within where the winds usually load the slide paths to trigger big enough avalanche to hit the road. The same with precipitation, the same idea. And here we're looking at this chart. The red line is basically when we threshold, so everything above it means we hitting thresholds. The green vertical line is where we're at right now, and let's look a little bit back, 24 hours back into the future. So in this chart, you can see 24 hours before we pull this chart, the 6 hour SWE interval actually was above thresholds. And when we have this system, it's really just a few lines of code, and you can actually put some text messages. So we get text messages every time we hit our thresholds, and every forecaster can sign up for what thresholds they want to have for which area. So we have warning. We know what's going on as long as everything works right. So to evaluate how it works, look at the Seven Sisters. And the Seven Sisters is a group of actually 8 slide paths. The east side of the Eisenhower Tunnel. It's a busy place. It doesn't take much for avalanches to hit the road, about 6 inches, sometimes 4 inches, and you get the road is buried. So we shoot it a lot. And we have a wind station just above Sister 1 and a snowtail site half a mile west of the Seven Sisters. So look at that data to see how well we did this year. And this is how well we did. So this chart, just to give you guys an idea, is the x-axis are 24 hours before and after the time we shot the Seven Sisters. The y chart is where we are as far as we compare to our thresholds. The red, the left side, is those avalanches, those avalanche mitigation where we hit the road, buried the road, and the right where we didn't bury the road. And the black line is the average. Does that make sense of all that mess? Good. So we can see that the 24 and 48 hours are much better predictors than the 6 and 12 hours. In a little better success with avalanches that hit the road than avalanches that don't hit the road. To take another look, I built those confusion metrics. And I don't know if you guys used those before. So just to explain a little bit, basically the horizontal side is actually those avalanche, that's the data itself, what happened after we shot. It tells me basically the lower is it didn't hit the road, the upper hit the road, and then the y-axis of vertical is what the model predicts. So on the left side it predicts to hit the road, and on the right side it didn't. And what we really want to look at is the diagonal. These diagonals tell us those two are the correct prediction, and the other direction are false predictions. And we want to see that upper left, lower right is as green as you can, and the other diagonal is as red as we can. And again, we see that 24 and 48 are very good. 75% success of actually predicting those avalanches to hit the road, and 2/3 or 66% when they didn't hit the road, and overall 70% success. So, one of the problems is actually when we try to measure it is we don't have a good way of measuring snowfall throughout a storm. Those ultrasonic units, they work great, but not for avalanche forecasters. The reason being is it makes a lot of noise, and when you look at it, it's always look like when it's heavy snow, and we really care to see what the snow is doing and how hard it snows. It tells us the snow is the height of the instrument because it reflects back from the snowflakes. So luckily for us in Colorado, we have a lot of ski areas, and no one believes the ski areas marketing department because they always hype up the numbers. So they put a lot of cameras everywhere on the snow stage. Yeah, what I did, I just stopped up in those images and built a small program that actually read the snow depth from the snow stakes. This is from Loveland Pass ski area, which we use a lot, and upper right is from Monument, which is actually one of our weather stations, where we put the camera. And then I can chart it, and you can see pretty heavy snowfall during the day, and we can actually measure it. There is no noise. So it seems to work pretty well. And this is, as far as, once you have that, you can also set your thresholds and get warning for thresholds. So, for example, I get warning when it's getting overnight, when we get 4.5 inches of snow, and then again 7.5. Those are thresholds I set. That's pretty much as much time it takes me to figure out, look at the weather, figure out if I want to close the road or not, or should have closed the road. But what's really exciting about this technology of actually using camera to measure snowfall, that we can measure it in the start zones. So if you have rocks or some sort of structure, you can measure it pretty easily as long as you have a camera that's looking at your structure and you know what the size of your structure. The reason we're excited about it because that's what we do when we measure snowfall in the valley and look at wind. We use it as a proxy of loading in the start zone. So hopefully this summer we're going to put a lot of cameras in start zone and going to start measuring that. That's going to be pretty nice.
Ron, can you explain a little bit more how that works? I'm confused how you get snow depth from the camera. Are you doing changes across?
I don't. I look at the stake itself. So what I do a little bit of image analysis.
Oh, you have a stake on the Kazakhs.
Yes.
Okay.
Or you can also look at the rocks as long as you know what the size is. And basically, the idea is to start seeing where the intensity of the pixel changes from dark or from whatever colors to white. And you just train your model a little bit.
So you do it manually to start, and then the model learns, and then...
No, this is a deterministic process. So I just do some analysis on the image, do some sort of adaptive thresholding. So it's try to increase the changes where it's snow and where it's not snow. And then once you isolate and you know the size of the area you're looking at, your stakes, it's pretty easy to recognize where is that changes from the stake itself to the snow, and you can compare that to the relative size of what it is when it's in the summer and see what bears and not. It's not very complicated at all. I don't do complicated stuff.
Did you have a way of looking at the star zones at night or just during the day?
So we looked into that, and we actually tested some pretty expensive equipment. It's a problem to look at it when it's snowing, when we care. So what we're doing, we're going to get a cheaper camera and install them closer to the start zone. And that's how we're going to do it.
Any type of light?
It's the IR camera, and you can find pretty cheap one with hunting camera, and you can light it if you want just for the image itself.
Gotcha.
Yeah. So when I got hired, the States gave me a computer, and I figured I might as well try to build something a little more sophisticated than just thresholding. And basically, I built a neural network to try to look at all the data 2 days before and every hour and try to forecast if we're going to hit the road or not. I use a recurrent neural network because it has the ability to actually look at processes over time and how things change over time. It's very popular with actually natural language processing, where something like sentence like Jimbo only drive truck is very, very different than only Jimbo drive truck. Those are very different sentences, but the same word. So we need to be able to actually look at things as they develop. Like for us, if we have 6 hours of snow and then the wind pick up, it's a little different than we have wind and then the snow pick up. It's a very different story. So I use this model, and now we run it in the background. It's very experimental, but we have basically that input on our website so we can look at it. And to some of the data, we have some issue. We have very small data. Those machine learning models, they like a lot of data. We like talking in millions. And we don't have a lot. And so, and then on top of that, we have some pretty dirty data. Like I told you, we have some problem with snow measurement. So I just use linear regression to fill up those gaps in data we don't have. And to overcome data problem we have, like we only have data when the forecaster decided to shoot the Seven Sisters. So that's a problem because they only have some sort of threshold in their mind. When it snows, they shoot it. When it doesn't snow, they don't shoot it. So the model doesn't really know what's happening where it's less than 4 inches of snow. They've never seen something like that. So they might get confused and start giving them more value, some other data that it's not as important. So I took a period of very stable snowpack we had in February and just injected as additional data when I was very, very convinced or confident we're not going to hit the road. And I trained it. And what happened, the data became very, very unbalanced. We have a lot of instances where we're not going to hit the road and a lot less than we're going to hit the road. So I needed to measure it in a different way. I couldn't measure it as far as accuracy, because if I look what's the chances of the model going to be right, it's going to be a bad way of measuring how well the model is doing. For example, if we're going to try to build a model and say, what are the chances you're going to have a Lamborghini parking outside this, the library? It's very, very low. So I can build a model that say it's never going to happen. And the model is going to be right, I don't know, 1,000 times out of, 9,999 times out of 1,000. And that's not a good model. So what I did, I use different metrics. So I use a precision, which is how well out of all the time the model predicts we're going to hit the road, how many times we actually predict the road. Recall, out of all the time they hit the road, avalanche should hit the road, how many times the model predicts we're going to hit the road. And then F1, which is a combination of both of them. And what we see here is basically, I charted it, and it looks pretty good most of the time. We had a few times where it was down to 70%. And the way I actually did it, I did what we call K-fold cross-validation. You take randomly 90% of your data, you train your model, you test it on the 10%. And you do it again, 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 again. I did it 20 times, so it gave me a good idea how it's doing on the entire data set, and give me some sort of distribution. I can look at it more than just one number. And talking about the F1, I know it's rude to show equation in avalanche talk, so this is the last time in this talk, I promise. So as always, there are some unintended consequences to that, to putting together a model and a warning system. One, I sleep slightly better at night, but when it's not, it's on the couch, because all those buzzes from the cell phone keep my wife awake. So just to summarize, it looks pretty promising. It gives us another fairly powerful tool to try to evaluate and figure out what we're going to do. We have a piece of data we can go back to. As far as thresholding, it's surprising how well it does. It's just one parameter when we're talking about interaction of several really complex systems coming together. And makes me a little worried, actually. We're going to have to keep on evaluating it as we go. It is, it'd be nicer to actually measure snowfall in the start zone and not just use whatever we can as a proxy. So a few years ago, I got an email from an ex-carpet patroller pointing me to a nice TED talk called "See Invisible Motion, Hear Silent Sound." And if you guys have a chance, Google it. It's pretty cool. This TED talk was about Eulerian magnification. Eulerian magnification is a smart and pretty simple algorithm to amplify small changes that are not visible in the video to the naked eye. Last fall, my wife took the kids to visit her parents in Houston, Texas. And I had a lot of time on my hands to write a small computer program that can do it. By the way, if there's one thing you want to take from this talk, don't go to Houston, Texas. To see the little hidden detail of avalanche release with Eulerian magnification, let's look at this video and see how it works. So here's a very slow down of the same video. On your left, you see the video when we did the Eulerian magnification, and you can really see stuff moving well before you can see it on the right side, before you start seeing those cracks develop. You can see the slab bending and how it leads to the avalanche release. And it's a good excuse to just watch avalanche videos again and again and again, and your family think you're crazy. It's like, hang on a second. Another example, a little muck around with the parameters. And here you can actually see there's some strain buildup here and here before it breaks. This ends here, where it's actually steep, which basically highlights how complex of a system we're dealing with, and maybe why our stability tests don't work very well everywhere. To look again, to compare, actually, I want to know that what we see is actually avalanche release, all this bending and not something else. So I'll look at this video from Alaska, and just hang on. Just to show you guys how it works, there's no magic here. The first step is basically we build some sort of pyramid, and what we do, we go and take every other row and every other column in the image and pull it out, create some sort of a smoothing up, create the normal image out of it, and then do it again and again and again. And the difference is the first video I show you guys, I only did the pyramid of 2 layers. The second one was of 5 layers. So it smoothed up a lot of things and actually can highlight different things in the picture. Also create that extreme changes in motion. The second step is we're looking at the pixel intensity. And pixel intensity is how bright the pixel is. When it's high, it's white. When it's very low, it's black. And here I'm looking at the changes in pixel intensity. And it's pretty easy to see what's going on here when we're looking at what we see is the average of this little square. We can see there's not much change in the first 40 or so frames. And then the crack probably start happening. It's getting darker. We see the pixel intensity drop. It's getting darker. At some point, it's open. The crack is wide enough. We get sun inside and see the bed surface. And the pixel intensity goes up. So what we're interested to see is what we can see in a normal video. So looking just at the first 40 videos, that's what we're going to look. And what we do is we take and actually fit a function to it so we can work with the function and see what's going on. The upper function is a Fourier transform, which is the original algorithm. It works really well when you have something that repeats itself, motion repeats itself, like someone breathing or blood going into in your veins and stuff like that. The lower one is a polynomial fit, which works better when you don't have motion that repeats itself. And the last chart is you basically take that and you can magnify it. This is 50 times as much, so all the changes are really well defined. You can see them. And the blue line, that's in the red line. The blue line is basically the changes as they are in the video. And just to give you guys an idea, I took, basically I modeled the blue line, and this is the middle of the grain between black and white, exactly in the middle, and amplified 50 times. You can actually see the changes that you will not be able to see otherwise. How it goes. And those frames are exactly the first 35, that's the timeline, is the first 35 pixels, as you see in the chart. So to make sure we actually see an avalanche before avalanche release and slab deformation, compare this slide video again from Alaska to this video. I believe this is a local skier. Doug?
Yeah, that's Ben.
I want to see what it looks like when we don't trigger avalanche. So just a quick look for those 2 videos. There's one really obvious thing we can say. Any idea? Skiing is safe, snowboard is danger. So this is what this avalanche release looked like when you magnify it. And what I did here, actually, I split it into grids. So every area I ran that process by itself to make sure that big changes not masking small changes. And you can see it really deform and goes to the side, not just underneath the snowboarder. So it's not just a slab from the snowboarder. And now you start seeing the avalanche release and cracks forming on the surface. Oh. I compared this one. This is 15 time, and you can see some movement on the trajectory of the skier, maybe a little bit of slack to the look left of it, of the skier. And the video is a little dirty, so it highlights some other stuff. But overall, it's pretty clear. I did 50 times just to make sure I'm not missing anything. And here, the skier looked a little more on flame. So that's the main difference. There's still we don't see any bending or any changing in the slab reflection going sideways. Again, this snowboarder, again, it's dangerous. He's skiing next to the avalanche, and again, we don't see, where there's some slab to the looker left, we don't really see that deformation in the slab going sideways. So I felt fairly encouraged when I saw that. And one thing nice about it, we can actually draw data out of those videos. So here you can see the intensity change inside of each one of those grids, how it changes over time. And here you can see the snowboarders start getting into this little square and intensity drops. The cracks start deforming and intensity start dropping on where it is, the cracks are. But what we're really looking at when we're looking at that time frame where before we start seeing cracks, when it seems like there's nothing happen, we're looking at the changes in intensity, where we can actually track the changes or where that chart looks a little steeper. So what I did the same thing, except I actually look at the absolute value of the derivative of the changes in the slab. So that's when we actually see steep changes. And what you see, I didn't tell you before, the blue line is basically the trajectory throughout the whole video. The red line is where we are right now for every frame. And once we look at the derivative, we can actually start highlighting where those changes happen throughout the video. So here you can see when the changes actually occurred during the avalanche release. And we can, every one of those grid size is about the height of the snowboarder. So with some assumption of how high the snowboarder, we can start actually calculating how fast those deformations in the slab occur and in which direction. And I did promise you guys there are not going to be any more equations, so I'm going to leave that to you.
So Ron, is there deformation like that just in a general skier going down where it doesn't trigger an avalanche?
So it seems like it's pretty close to the skier, but you don't really see it shooting to the sides.
Like this.
Yeah, so you see it around the skier. Another few things that seems like interesting from this video is it seems like the deformation speed changes as when you actually, with the orientation to the slope. There are some areas that you don't see deformation till actually a while. It seems like the deformation kind of goes around some area and then pull them out. I can try to run it again. Which is something that we kind of suspected for a while. That's maybe the deformation, or I'm having a hard time to say confidently it's actually that's the deformation that create the crack propagation. But you can see areas that don't deform very fast, and eventually they get pulled. So we talked about that. We don't really know. It's probably not a straight line as far as deformation and crack propagation from point of initiation to the boundary of the slab. Boundary of the slide, there might be stuff going around or some stuff that never really released till it gets pulled by the rest of the slab. The reason I came here is actually to hear the other speakers, so I'm going to cut it here.